A quantum leap introducing the Majorana chip. The world stood still, scientists gasped. We had entered a new era. This was the dawn of the Majorana 1000-Qubit quantum chip. This wasn't just an upgrade, it was a revolution. The chip promised to shatter the limits of computation. It beckoned us to a future brimming with unimaginable possibilities. For decades, quantum computing remained a distant dream. It was a tantalizing concept forever on the horizon. But the inherent instability of traditional qubits held us back. They were fragile, prone to errors, and difficult to scale. The Majorana chip changed everything. It ushered us into a new realm of quantum supremacy. This chip wasn't just about speed, it was about exploring the very fabric of reality. It held the potential to unlock secrets of the universe that had long eluded us. We stood on the precipice of a new age. This was an age of discovery, driven by the power of the Majorana chip, where hardware meets software, a symphony of innovation. The Majorana chip was a marvel of engineering and ingenuity. It was a testament to the seamless integration of cutting-edge hardware and sophisticated software. At its heart lay a tapestry of superconducting nanowires. These nanowires, cooled to near absolute zero, served as the stage for a quantum ballet. Within these frigid circuits, Majorana fermions emerged, quasi-particles that acted as the qubits of this revolutionary system. These were not your ordinary qubits, prone to errors and decoherence. Majorana qubits were robust, maintaining their quantum states with unprecedented stability. Orchestrating this intricate dance was a symphony of software. This sophisticated software allowed us to control and manipulate the Majorana qubits with remarkable precision. Algorithms, specifically designed to harness the power of these unique qubits, unlocked computational possibilities previously unimaginable. This harmonious fusion of hardware and software was the key to the chip's power. It allowed us to tap into the strange and wonderful world of quantum mechanics, pushing the boundaries of scientific exploration further than ever before. The enigmatic Majorana fermions, particles beyond the veil. At the heart of this technological marvel lay the elusive Majorana fermion. First theorized by Italian physicist Ettore Majorana in 1937, these particles remained elusive for decades. They were ghosts in the quantum machine, particles that were their own antiparticles. Unlike electrons or protons, which had distinct antimatter counterparts, Majorana fermions occupied a strange duality. They were both matter and antimatter simultaneously. This unique property conferred upon them an inherent stability that set them apart in the quantum realm. When trapped within the superconducting nanowires of the Majorana chip, these exotic particles revealed their true potential. They became the building blocks of a new kind of qubit, one far more resilient and less prone to errors than traditional qubits. This stability was the key to unlocking the power of quantum computing on an unprecedented scale. The Majorana chip, with its heart of enigmatic fermions, was not just a technological marvel. It was a portal to a deeper understanding of the universe's fundamental building blocks. The Majorana chip's true brilliance lay not just in its use of Majorana fermions, but in the advantages they offered over traditional qubits. Traditional qubits, based on trapped ions or superconducting circuits, were notoriously fickle. They were susceptible to environmental noise, leading to errors that plagued quantum computations. Majorana qubits, on the other hand, exhibited remarkable stability. This robustness stemmed from their unique topological properties. Information was encoded not in the state of a single particle but in the collective state of multiple Majorana fermions. This made them far less prone to decoherence, the bane of traditional quantum computing. This stability was not the only advantage. The Majorana chip's architecture allowed for scalability that was previously unimaginable. Thousands of Majorana qubits could be integrated onto a single chip, paving the way for quantum computers of unprecedented power. This scalability opened up new frontiers in scientific exploration and technological innovation. The stability and scalability of the Majorana chip were game changers. They promised a future where quantum computers were no longer confined to research labs, but became an integral part of our technological landscape. The Majorana chip was more than just a technological leap. It was a journey into the unknown. As we pushed the chip to its limits, we began to encounter the truly bizarre. The results of our computations were not always what we expected. At times they seemed to defy logic, hinting at a reality far stranger than we had imagined. One of the first anomalies we observed was what we dubbed computational hauntings. These were persistent patterns in the output data that seemed to have no correlation to the input. They were like whispers from the quantum void, echoes of computations past that lingered within the chip's architecture. These hauntings, though initially unsettling, were not entirely unwelcome. They suggested that the Majorana chip was not merely processing information, but interacting with reality on a fundamental level. It was as if the chip was no longer just a tool, but a window into the hidden workings of the universe. These strange occurrences were just the tip of the iceberg. As we delved deeper into the Majorana chip's capabilities, we encountered even more perplexing phenomena that challenged our very understanding of reality itself. As we ventured further into the uncharted territory of the Majorana chip's capabilities, we stumbled upon an even more perplexing phenomenon: temporal anomalies. At first they appeared as subtle glitches in the system, inconsistencies in timestamps and data logs. But as we investigated further, a chilling realization dawned upon us. The chip seemed to be interacting with time itself. In one particularly startling experiment, the chip consistently predicted the outcome of random events, from stock market fluctuations to the outcome of dice rolls. It was as if the chip had tapped into a hidden temporal stream, accessing information from the future to inform its present-day calculations. These temporal anomalies were not merely a scientific curiosity, they raised profound philosophical and existential questions. If the chip could access information from the future, did that mean free will was an illusion? Were we merely pawns in a predetermined cosmic game, our choices already made? The implications were staggering. The Majorana chip was no longer just a tool for computation. It had become a window into the nature of time itself, a Pandora's box of temporal paradoxes and mind-boggling possibilities.